Hi everyone. Today we are starting section 2.4, continuity. One of the most important ideas in calculus. A function is continuous if its graph can be drawn without lifting your pencil from the paper. Today we are going to make that idea precise. Before we jump into the formal definition, let's think about what it means for a function to be continuous at a single point. If I say a function is continuous at some number x equals a, what does that really mean? It means there's no break, hole, or jump in the graph at that point. Nothing strange happens there. But in calculus, we don't just rely on pictures. We need a precise definition. So here it is. A function is continuous at x equals a if and only if three conditions are satisfied. Let's go through them one by one. First, the function must actually exist at that point. So if I plug in a, I should get a real number. If f of a is not defined, maybe there's a hole in the graph, then the function is automatically not continuous there. So step one, the function value must exist. This graph is an example where f of a is not defined. Second, the limit as x approaches a must exist. That means the left-hand limit and the right-hand limit must equal. If the function jumps, meaning the left side approaches one number and the right side approaches a different number, then the limit does not exist. If the limit does not exist, continuity fails. So step two, the limit must exist. This graph is an example where the limit does not exist at x equals a. Finally, and this is very important, the limit must equal the actual function value. So in symbols, we need limit of f of x as x approaches a equals f of a. So even if the limit exists, and even if f of a exists, they must match. If they are different, the function is not continuous. This graph is an example where f of a does not equal the limit at a. Now look at the fourth graph. This is an example where the function is continuous at a. Notice the closed dot fits exactly where the graph approaches. The limit and the function value match. Everything connects perfectly. So in summary, a function is continuous at x equals a if the function value exists, the limit exists, and they are equal. If all three conditions are satisfied, the function is continuous. And if any of them fails, the function is discontinuous at that point. And that's exactly what continuity at that point means. Now that we know the definition of continuity, let's turn it into a three-step strategy we can use when solving problems. Step 1. Check if f of a is defined. If the function value does not exist, the function is not continuous. Step 2. Compute the limit as x approaches a. If the left and right limits don't agree, the limit does not exist, and the function is not continuous. Step 3. Compare the limit and the function value. If they are equal, the function is continuous. If they are not equal, the function is not continuous. So whenever we check the continuity at a point, we simply follow these three steps. Now, let's look at a few examples to see how we check continuity in practice. Remember, When we check whether a function is continuous at a point, we follow three steps. First, check if the function value exists. Second, check if the limit exists. And third, compare the limit and the function value. So let's try example 1. Determine whether the function f of x equals x squared minus 4 all over x minus 2 is continuous at x equals 2. So step 1, I want to know if f of 2 is defined. I will substitute x with 2 to find the value of f at x equals 2. F of 2 equals 2 squared minus 4 all over 2 minus 2. In the numerator, I have 2 squared minus 4. 2 squared is 4 and 4 minus 4 is 0. In the denominator, I have 2 minus 2, which is also 0. If we plug in x equals 2, the denominator becomes 0, so the function is not defined at x equals 2. Since the function is not defined at x equals 2, the function is not continuous at x equals 2. Now, let's look at another example. We want to determine whether the function f of x is continuous at x equals 3. To check for continuity at x equals 3, first we need to check f of 3. We will replace x with 3 to evaluate f of 3. This function f of x is a piecewise function. We have two different formulas. We will use negative x squared plus 4 if x is less than or equal to 3. And we will use 4x minus 8 if x is greater than 3. Now, I want x to be 3. So x is less than or equal to 3. I will use this formula, negative x squared minus 4. So if I replace x with 3, I will have negative 3 squared minus 4. So I have f of 3 equals negative 3 squared plus 4. 3 squared is 9, so it'll be negative 9 plus 4. And negative 9 plus 4 is negative 5. F of 3 equals negative 5. So yes, f of 3 is defined. Now, we need to move on to the next step. Check the limit as x approaches 3. To find the limit of f of x as x approaches 3, we need to find the left-hand limit and the right-hand limit. This is the notation for left-hand limit. We use the little minus sign here, indicating that x is approaching 3 from the left. And when x is approaching 3 from the left, that means x is less than 3. This is the function f of x. We will pick this formula because x is less than 3. This is a polynomial. To find the limit when x approaches 3, I simply substitute x with 3. Negative 3 squared is negative 9, plus 4 is negative 5. The left-hand limit of f of x equals negative 5. Now, let's find the right-hand limit. This is the notation for the right-hand limit. I use the little plus sign here, indicating that x is approaching 3 from the right. When x is approaching 3 from the right, that means x is greater than 3. We will use this formula, 4x minus 8. 4x minus 8 is a polynomial. To find the limit when x approaches 3 from the right, we substitute x with 3. 4 times 3 is 12, and 12 minus 8 is 4. The left-hand limit is negative 5, and the right-hand limit is 4. They're not equal. So the limit of f of x as x approaches 3 does not exist. Since the limit of f of x as x approaches 3 does not exist, the function is not continuous at x equals 3. Now, let's look at one more example. Determine whether the function f of x is continuous at x equals 1. Step 1. Check the function value f of 1. To find f of 1, I use f of x and I replace x with 1. F of x is a piecewise function. It will be 2x plus 1 if x is less than 1. It will be 2 if x equals 1. And it'll be negative x plus 4 if x is greater than 1. Now, my x is equal to 1, so I'm using 2. F of x will be equal to 2 if x equals 1. So f of 1 equals 2. That means my function is defined at x equals 1. Next, let's compute the limit as x approaches 1. To find the limit of f of x as x approaches 1, I need to find the left-hand limit and the right-hand limit. For the left-hand limit, x is approaching 1 from the left. That means x is less than 1. When x is less than 1, I'm using 2x plus 1. Limit when x approaches 1 from the left of 2x plus 1. I will substitute 1 in for x. So I have 2 times 1 plus 1, which is 3. Now, let's find the right-hand limit. For the right-hand limit, x is approaching 1 from the right. That means x is greater than 1. When x is greater than 1, I'm using this formula, negative x plus 4. And I will substitute x with 1. I'll have negative 1 plus 4, which is 3. The left-hand limit of f of x is 3. And the right-hand limit of f of x is also 3. That means the limit of f of x as x approaches 1 is 3. Since the limit of f of x as x approaches 1 is 3, so the limit exists. Finally, step 3, we'll compare the function value with the limit. Is f of 1 equal to the limit of f of x as x approaches 1? F of 1 is 2. And the limit of f of x as x approaches 1 is 3. They are not equal. So the function is not continuous at x equals 1. These three examples show the three ways continuity can fail. The function value may not exist. The limit may not exist. Or the limit may not equal the function value. Whenever you check continuity at a point, just follow the same three steps.